Our next speaker is Professor Kapil Paranjape. I'm very happy to see him. He was our former colleague here, and we really miss him after he left here. So, welcome, Kapil. And he will be speaking on cycles in Chennai. Very interesting topic.
So first of all, let me thank the organizers for inviting me to this 60-year celebration, and also for choosing the day which is actually happens to be the birthday of Mad Science. Mad Science was, as Sudeshna has already said, Mad Science was in many ways the second formative institute for both of us, TIFR being the first. And so as they say, first you are a graduate student and you learn a lot from others. And in the second stage, you teach others. And in the third, you do research with others who are your graduate students. And then now we are in the third stage where we are teaching undergraduates. So it's an experience. And so, before, though the title is Cycles in Chennai, it's not really about cycling. Even though as it happened, when we were in Chennai, we used to, in those days, cycle. Almost all the people I'm going to talk about used to actually come to the institute by cycle. But the talk is not about cycling. So I thought, since this is an occasion to talk about the work which was done in IMSC in a certain seminar, so I want to explain some work which was done with graduate students and postdocs at Chennai. And so let me start. Let me start with what is called the Abel-Jacobi homomorphism. So the fundamental theorem of algebra says that if you take a meromorphic function on the Riemann sphere, then it has the same number of zeros as it has poles. Of course, there's always this caveat that you are supposed to count the number of zeros and poles properly, which I will ignore. And this result extends to a compact Riemann surface, which is also known as a smooth projective curve, X. And the question is there a converse, right? So that is the question which was in some sense posed to Abel and Jacobi, or they posed it to themselves. And in other words, given a finite collection of points, Pi, on a compact Riemann surface, so I had thought that I'll use my own laptop, in which case I would have drawn a Riemann surface, but by now you have seen the talk by string theorists, and they have already introduced what is a compact Riemann surface to you, so I don't need to do that. Given a collection of points on a compact Riemann surface, and with associated integers ni such that sigma ni is 0, is there a meromorphic function with exactly these zeros for ni bigger than 0? So ni is the order of the 0, and when ni is negative, then it's the order of the pole, or minus ni is actually the order of the pole. Okay, so the question which we are asking ourselves is, when can we say that there is such a function? And this was answered by Abel and Jacobi. And in modern language, the question is posed as follows. So you introduce a certain group, which is called the group of divisors, which consists of formal linear combinations of these points. Just formally, you write it as a sum. Of course, you can't add points on a Riemann surface in any reasonable sense, but you can certainly such a formal sum. And then we use kx star to denote the group of meromorphic functions, non-zero meromorphic functions, I should have said. And you define the map which associates to each meromorphic function, which is divisor of zeros and poles, and that gives a certain map from one group to another group, and one can rather easily prove that this is a group homomorphism. And we can also define a map which is called the degree, which associates to a divisor. Just you forget the points and just take the sum. Remember that we are only allowing finite sums, and therefore the answer you get is finite. And so what we are interested in asking is, we can call it the exactness of the following sequence of abelian groups. Okay, so for those who don't know where this term exactness came from, so I got this idea from beforehand, but how is the term exact come? And the exact comes from something which we know in calculus, which is we ask this question, when is the divergence, given that the divergence of a vector field is 0, is this the gradient of a function? In other words, whether it is exact, and it's from there that the term exactness comes from for exact sequences, right? So, and it's an example, I mean, in some sense, that's a very typical example for us to understand exactness of a sequence. Okay, so we are asking for the exactness of the sequence, and of course the answer is that it's not exact. So if I look at the divisors which are of degree 0, which means that those elements, those formal sums sigma ni pi, where sigma ni is 0, we can ask what happens to this group, right? So this is the group, and then we are going to go modulo those which come from the divisors of functions, and the answer is that what you get is a certain compact complex torus called the Jacobian in honor of Jacobi, and that is the compact complex torus, and the kernel of this Abel-Jacobi map, phi, which I don't have time to describe but is rather explicitly described in terms of certain integrals, is precisely the divisors of functions. Okay, so this gives a complete answer in this case of the original question by saying that when we know exactly when a certain some sigma ni pi is 0. If sigma ni is 0, we know when it is the divisor of a function, and the answer is if the image under the Abel-Jacobi map is the 0 element of a certain compact complex torus, which is also in a group, right? So, by the way, this has some connections and of this theorem to complex analytic representations of fluid flow to fluid mechanics and electromagnetism on surfaces. And more recently, I suppose, this is something which has become of interest to string theorists. But there is a classical relation with physics as well. And that was explored a little bit by Riemann, anyway. So the study of algebraic cycles, and which is what I'm going to talk about, cycles in Chennai refers to algebraic cycles. So I got you in here on false pretenses, is to generalize this classical theorem. So that's what is the question, one of the main questions of algebraic cycles that we are, oops, it doesn't seem to go back. Now, so we should think of this group Jacobian of X as a kind of obstruction. Okay, it's an obstruction to saying that some problem has a solution, because if the image of sigma ni pi in this group is non-zero, that means there is no such function. So this group measures how far it is, or gives you an obstruction from to construct such a function, right? So obstructions were recognized as a way of understanding questions in topology. In fact, Parmesh's student yesterday mentioned this, that the difficulty of deciding whether two spaces are equal or not comes from the question of whether certain groups are equal or not, and therefore topology provides what is known as an obstruction theory. Doesn't mean that when the obstructions vanish that the problem vanishes, but it certainly means that if the obstruction doesn't vanish, then the problem has no immediate solution, right? So we can see the Jacobian as a group of obstructions to finding meromorphic functions as required. And topology is a way, oops, what happened? And topology is a way to study these obstructions to the existence of certain geometric objects. So to every pair of topological spaces, topology associates a sequence of abelian groups Hn, x, y, which satisfy various properties, which I won't go into. This is called the Eilenberg-Steenrod axioms for cohomology. And when y is equal to 0, we write this as Hn of x. So yesterday in the lecture by Manas, I think you saw some of these examples being calculated somewhat explicitly. We are talking about them for topological spaces, but just to give you for algebraic varieties, but just to give you an example, the fact that H2 of the sphere, the ordinary sphere is integers, which is a non-zero obstruction, shows that in fact the sphere cannot be flattened, right? Which we know from intuition, but if you want a mathematical proof, then this is one of the ways you can prove it. Okay, so let me come to Nori's category of motives, which is a vast generalization of this idea of obstructions. Which of course, yeah, I mean, it's not as if he drew it out of nothing. But in any case, Srinivas is here. I think he may be the only person here who was in that seminar. The rest of them will be named shortly, or some of them. In a meeting in IMSC in the early 2000s, I don't remember the exact date, Madhav Nori came here and explained his construction of a universal cohomology theory for algebraic varieties. Unfortunately, it took a long time before it was written up, and now it's been written up, and there is a book on the topic by Muller Stark and Annette Huber, which I should warn you contains a few gaps, but otherwise it's okay, which explains Nori's theory of motives. And you will also find, if you go to the AMS Open Notes website, a course which I gave on this topic at WashU in 2019 called Motivic Linear Algebra. So what does it do? It constructs a certain group called the Motivic-Galois group, and what one shows is that given a pair of algebraic varieties y and x, y is the subvariety of x, well, it's more general than that. Perhaps one can also talk about schemes and so on, but it's not very important here. The associated h and x, y are representations of this group, okay? So, contrary to what you may have got the feeling from the previous talk, this group is ridiculously large. We are not talking about simple things like finite groups, though, as she pointed out, finite groups are not as simple as we think, but this is a really large group. And so it's not as if we can immediately say much about what these representations are, but in any case, that gives a certain structure to whatever we are looking for, okay? And that's the important thing. So the main point is that geometric maps gives rise to G equivariant maps between representations. So she talked about isomorphism, but here we are going to talk about maps between representations which satisfy the same commutation relation which she wrote, except that it's not an isomorphism, right? So there are linear maps between representations, and this construction partially solves the question which was posed by Grothendieck, which was to construct such a group. Since Srinivas is here and he would have pointed it out, I would say that I'm cheating a little bit because the original cohomology theory has integer coefficients, but when we say that there is a group, we are actually using Q coefficients. Okay, we are using rational number coefficients. Otherwise, you have to be a little careful, and it's not really a group, but it's a monoid. Okay, but doesn't matter. However, we have not been able to prove all the required properties of this group and its category of representations. Okay, it's a big category, and it's a big category of representations, and we would like to understand it in various ways, and various attempts have been made to understand various aspects of this group. Okay. So one of the things which you can do with groups which are not finite is we can talk about extensions. Okay, in the case of finite groups, especially if you are working in finite groups with representations over complex numbers, as was being done in the previous lecture, every representation can be written as a direct sum of irreducible representations. However, this is not the case for a general group, okay, and in particular not for this Motivic-Galois group. So given a subspace, of course, of a finite dimension, I should have said somewhere finite dimensional, so all my vector spaces are finite dimensional here. You can always find a supplement, right? You can find a subspace which is of the complementary dimension and such that the intersection is 0 and the sum of the two is the whole thing. However, when we are looking for a sub-representation, the supplement may not be a sub-representation, and this is what gives rise to what are called extensions of representations. Okay, so we get an extension of W by U. So of course, you can think of U as W mod V, and therefore you do have 3 representations and an exact sequence of the kind I had written earlier, but which does not, in the language of extensions, does not split. Okay, so there are non-trivial extensions in the category of representations of this large Motivic-Galois group, and that's one of the important points. So representations of this group G can have non-trivial extensions as it is not a reductive group. So reductive groups generalize the notion of which we commonly have of finite groups, that every representation can be written as a direct sum of irreducible representations. This is not true in general, and examples are the additive group, for example, is not reductive. Okay. In fact, the Jacobian can be seen as an extension of this kind. So I haven't told you what this object is, but doesn't matter. I will forge ahead. And the Jacobian can be seen as such an extension group, in fact. Okay, and so this is the nice thing, that suddenly we have now turned a question of topology. By using Nori's category, we have converted it into a question about representations of a group and asking whether certain obstructions exist for the extensions to split and non-split, right? So cohomology is a special case, or what we are saying is that this cohomology theory which we are looking for is actually like the cohomology theory of a certain group, which is always nicer than general cohomology theories. Okay. So the group of formal linear combinations of points on a smooth projective variety then carries a certain filtration, and this filtration has the property that the associated gradients are, so we had X1, but in fact in this Nori's category of motives, we expect and we can show in various X groups exist. So there's X1, X2, X3 and so on. And so each of these filtrations, so on this formal group, we have a filtration by subgroups, and the quotient groups are themselves X groups. So you can see that what we are asking is whether things become zero in each of these extensions. So asking whether the Jacobian element is zero is asking whether the X1 element is zero. But then you could have an X2 element and you could have an X3 element and so on. And we could ask whether all the X elements are zero, then something would happen. Okay. But now one thing is clear from the general theory of cohomology, that there are no cohomologies in negative dimensions. So therefore H2D is the dimension of the variety, then H2D minus P is zero for P greater than 2D. The reason D becomes 2D is because when you're working over algebraic varieties, the dimension is counted in terms of complex dimensions, and so the complex dimension is 2D rather than D, right? So it's a dimension over complex number of the solution space over complex numbers. But in fact, it is expected that this X group is zero for even P greater than D. However, we haven't actually proved any of these statements, but we expect therefore there to be a geometric meaning for FD plus 1. Okay, and that geometric meaning is through the notion of rational trivial cycles. Okay, so probably Srinivas will talk a little bit more about this in his talk. Rationally trivial cycles are the higher dimensional version of divisors of a function. Okay, so that's the idea. The idea is that this FD plus 1 should have a very concrete geometric meaning. Okay, and we expect, but at the moment we are unable to prove that FD plus 1 is exactly rationally trivial cycles. So that's what we would like to prove. And Bloch's conjecture for surfaces is the refined version of this statement. So Bloch's conjecture was for surfaces says that exactly as we want for curves, we know that F2 is 0, is exactly what we know for curves for d equal to 1, and the analogous conjecture would say that what do we expect for d equal to 2, and we expect F3 to be 0. And Bloch's conjecture refines this a little bit more. I won't actually get into the refinement here. As a conjecture, this has been generalized to all varieties through the work of Beilenson and others. So this is one of the amazing things about the theory of algebraic cycles, that the very first generalization that we had of Abel-Jacobi, which is the conjecture of Bloch, has not yet been proved. But we have no problem generalizing these conjectures to even further bigger conjectures over all varieties and so on. Okay, and but the point is that it fits very nicely into a general framework. So We don't know any counterexamples. In the language of physics, we proved this conjecture. Okay, because for 25, 30 years, we haven't found a counterexample. So in that sense, we can see, not only that, it's consistent with all the other things that we have understood about varieties in the meanwhile. However, we don't actually know how to prove this. However, there are very few results proving this, even in isolated cases. There are some results. Now, there is a category called the category of mixed Hodge structures, which was introduced by Deligne. And in fact, the HNXY are elements of this group, this category, which is a slightly bigger category, quite substantially bigger category than the category of constructed by Nori. And it was known before the construction of the category M of motives, Nori motives, that the Jacobian can be seen as an extension group in this category. Okay, and so Green constructed a certain, decided, okay, can I just use, rather, because when Green did this work, Nori's category had not yet been constructed, or certainly its construction was not that well known. And so he wanted to construct X2 using Hodge theory directly, rather than go through this elaborate construction due to Nori. And Voisin was able to show that Green's conjectured construction doesn't work. Okay, we got to know in our cycle seminar almost simultaneously both about Voisin's paper as well as about Green's construction. And we had this feeling that whatever Voisin had done, of course, Voisin is an outstanding mathematician, was far too complicated, and it should be much easier to prove that Green's construction is wrong. Okay, and the seminar on algebraic cycles was one of the activities at IMSC that started here to study these ideas. Okay, so the first thing we did in collaboration with Jishnu Biswas, Gautam Dayal, and G.V. Ravindra. I should say that Jishnu is a faculty member at the Indian Statistical Institute. Gautam Dayal, whose footsteps in some sense I may have followed, is a teacher in Shrishti, in a school in Bangalore. And G.V. Ravindra is a faculty member at University of Missouri, St. Louis. So they were all here. Jishnu as a postdoc and Gautam Dayal and Ravindra as students. And we showed that Green's construction amounted to construction X2. So one of the things you can do in homological algebra is to see that X by extensions can be constructed by pairing together one extensions. And so X2 can be constructed using X2, using two X1 elements. Now this description, there's nothing wrong with it. There is an X2 element which can be constructed using X1 elements. But the problem with Green's construction was that in the process of constructing X2 out of X1 and X1, he was killing a very large subgroup of X1 tensor X1. Okay, this is the problem. And we were able to produce it should say, not product. We were able to produce many counterexamples to Green's construction that were conceptually much easier to understand than Voisin's example. As a side note, I should remark that after doing this, I visited Green and met him for the first time. And of course, we had collaborated earlier on various projects, and his graduate student was a little bit annoyed. The first time you're meeting him, you're telling him that his conjecture is wrong. That was not appreciated by his graduate student, but Green, in fact, appreciated it. And he said, let's work on some more stuff. So now I'm going to talk about what I did with Green and Griffiths on this second aspect. So one thing we can do is, instead of studying varieties as we have done over complex numbers, we are looking at Riemann surfaces, but you could look at those which are defined, geometric objects which are defined over rational numbers, okay? Or over small fields like fields of transcendence degree 1 or 2 or 0 over number fields. Now, on the one hand, there are fewer geometric objects because, of course, you want your equations to all the functions, everything to be defined with rational coefficients rather than complex numbers. On the other hand, we also have fewer maps because the maps also have to have rational coefficients. So what does this do to the group? So this is not very clear a priori what it does to the group, right? So now we are restricting our attention only to varieties and morphisms defined over a small field. Does that increase the group? Does that decrease the group? How does it constrain the group? This too was a topic of conjecture due to Bloch. And Bloch conjectured in this case that the second term in the filtration is 0 for all varieties. And currently, as far as I know, one of the examples we have of this case is due to Krishna and Amlendu Krishna and V. Srinivasu in the audience, where this is known to be true. Of course, I'm fudging a bit because I think their example is of a singular variety, whereas I have only stated everything for a smooth variety. But in principle, that is the kind of example where one knows certain results of this kind. We don't really know it in general. So what happens when we increase the transcendence degree of the field? What happens if we take, instead of Q, we take a field with one transcendence variable or more transcendence variables? And so we also expect that Ft plus 2 is 0 where the field of transcendence degree T over Q. Okay, so this is another of the expectations. Perhaps Srinivas will mention this a little more tomorrow. I don't know, he's nodding his head saying no, but in any case. So in collaboration with Mark Green and Phil Griffiths, it was shown that F2 is non-zero of fields of transcendence degree 1. So in other words, it's not that you can make F2 0 for a field of transcendence degree 1, right? So F2 was supposed to be 0 for fields of transcendence degree 0, which means over Q or number fields. But as soon as you increase the transcendence degree by 1, F2 is in fact non-zero. And it would be actually, just when I was writing this lecture, it occurred to me that perhaps one should ask some graduate student to take it up as an interesting problem to try to generalize this result, which was proved with Green and Griffiths. We used an idea of Nori that had already been used in a special case in the work of Schoen to prove this example. And one can, of course, go on to study higher dimensional cycles. Instead of studying points, you can take formal linear combinations of subvarieties and you can ask the same question. But one of the interesting things is that there's a famous paper of Nori called, I think, Hodge theoretic connectivity, and in which it is essentially shown, again, based on conjectures, that you can reduce the problem from higher dimensional varieties, subvarieties to zero dimensional varieties. And since Srinivas in the audience, I must say that he was the one who always told me how important zero cycles are. And this theorem underlines this aspect. So the seminar on algebraic cycles, of course, as the postdocs moved to get faculty positions and the students moved to get postdoc positions and so on, ultimately disbanded. And then after that, but that was one of the things we spent a lot of time on in Chennai in the early 2000s with all these wonderful people like Jishnu Biswas, Gautam Dayal and Ravindra. And we had various visitors. I think Srinivas was here, Ellen Eno came here, and Eckhart Fieweg, the late Eckhart Fieweg came here, and so we had, and Andreas Rosenschön came here, and so on. And we had a lot of activity at IMSC under this cycle seminar. And I thought I'll highlight two of the important results which came out of this, and I'll stop with that. Thank you.
So we were also cycling at that time from Leelavati to here.
Incidents, somehow, that it was not intended by any of the members of the cycle seminar, but as it happened, it happens to be factually true that everyone in the cycle seminar used to actually cycle from Leelavati or wherever they were staying in the city to Mad Science. Thank you.
Thank you.